You ever wonder how our computer chips just keep getting more and more powerful? I mean, they're powering everything from our phones to this huge AI revolution. Well, the answer isn't what you'd think. It's not about making one giant, super powerful chip anymore. Nope. It's actually about breaking them apart. Today, we're diving into chiplets, the microscopic Lego bricks that are completely rebuilding modern tech from the ground up.
It sounds totally backward, right? A complete paradox. For decades, the whole game was about cramming more and more transistors onto one single giant piece of silicon. But to get to the next level of performance, engineers did the exact opposite. They shattered the chip into a bunch of tiny pieces. So let's explore why that seemingly crazy step was actually a massive leap forward.
To really get it, we have to look at the problems with the old way of doing things. You see, the industry wasn't just hitting some metaphorical wall. It was a hard, physical barrier that engineers just could not get around.
And this right here, this is that wall. The equipment that's used to manufacture chips can only print a pattern up to a certain size, about 860 square millimeters. Think of it like this. It's the maximum size of a photo you can develop from a single film negative. Once you hit that reticle limit, that's it. You literally can't make the chip any bigger. And if you want more power, you need more silicon. But the manufacturing process itself was basically saying, nope, this is as big as you get.
This also brings us to a massive manufacturing problem called yield. Okay, imagine you're baking a giant pizza-sized cookie. The bigger that cookie is, the more likely a crack is going to show up somewhere and ruin the entire thing. Well, it's pretty much the same with these big silicon wafers. A single microscopic speck of dust can make a whole massive processor completely useless. So the bigger the chip you try to make, the higher the chance of a really expensive fatal flaw.
And this gets right to the heart of the economic problem. With one giant chip, a single tiny defect means you have to throw away an incredibly expensive piece of hardware. But if you make dozens of smaller chips instead, a defect only ruins one cheap little part. You just toss that one flawed Lego and keep all the other perfect ones. All of a sudden, the financial risk just plummets.
So you're faced with a physical size limit and this massive financial risk problem. The industry needed a really clever solution, and that solution was to embrace the small, which led to this chiplet revolution. It's all about building bigger by first thinking much, much smaller.
So here's the core idea. Instead of designing one huge do-it-all chip, what they call a monolithic chip, engineers break it down into its core functions. You end up with small chiplets just for processing, other little chiplets for handling data, and even tiny chiplets for memory. Each one is a simple, specialized expert. And then you just assemble these perfect little experts together inside a single package, and they all work together as a team.
So the process ends up looking like this. You start by producing tons of small, simple dies. Because they're small, the success rate, that yield we talked about, is way, way higher. This gives you this huge bin of perfect working pieces. You then just combine those working pieces to create these monster GPUs and CPUs that are far more powerful than anything that was possible with the old monolithic system. Of course, having a bunch of tiny chips is pretty useless if they can't talk to each other fast. The real magic isn't just making the chiplets, it's the incredibly sophisticated technology that connects them all seamlessly, making them act like one single, unified brain.
Think of it like an all-star team. You've got your compute dies, these are the geniuses doing all the heavy math. Then you have the I/O dies. They're the expert communicators managing all the data traffic flowing in and out. High bandwidth memory, or HBM, is like the super-fast personal assistant, feeding data to the brains instantly. And holding this whole team together, letting them all communicate, is the interposer.
The interposer is really the unsung hero of this whole operation. It's not just some tray that holds all the chiplets. It's a highly complex piece of silicon itself, crisscrossed with thousands of microscopic, high-speed data highways. It's the advanced communication network that allows all the different specialists on the team to work together in perfect sync.
But to make sure all these different pieces can actually work together, especially when they might come from different manufacturers, the industry needed a universal standard. That's UCIe. It's basically the common language, the universal translator that lets a chiplet from one company talk perfectly to a chiplet from another. And that just opens up a whole new world of design possibilities.
Okay, so we've covered the why and the how. But what does all this mean in the real world? Why should you actually care about these tiny building blocks? Well, it turns out this technology is directly powering the biggest tech trends of our time.
I mean, this quote just says it all. The AI revolution, the large language models, all the AI image generators, all of it runs on massive power-hungry GPUs. And those GPUs, the most powerful ones on the entire planet, simply could not exist without chiplet designs. Chiplets are the fundamental hardware that's enabling the AI software we're seeing pop up everywhere today.
And beyond just AI, this whole approach helps companies bring new products to market way faster. They can mix and match components, like upgrading the brains while reusing the same data connectors. It also lets them easily create a whole family of products. So a Pro model might have 12 chiplets, while a light version of the same thing only has 6. And yep, this modular design is also the core tech behind the world's fastest supercomputers. Now, it's really important to understand that chiplets aren't some kind of magic bullet. This new design solves a lot of old problems, but wouldn't you know it, it also creates a brand new set of very difficult engineering challenges. There are always trade-offs. So here are the big 4. First, latency. Even at the speed of light, it just takes a tiny bit longer for a signal to travel between 2 separate chiplets than it does to travel inside one single chip. That communication also uses extra power. And packing all these high-performance parts so close together creates intense little hotspots that need very advanced cooling. And finally, the whole process of assembling these microscopic Legos is just incredibly complex and delicate.
So, the crucial point to take away is this. Chiplets have their own challenges, absolutely. But the old way, the big monolithic chip, that hit a dead end. The new challenges of chiplets, things like latency, power, and heat, these are problems that can be engineered and innovated around. They represent the necessary and really the only path forward to keep pushing the boundaries of what computers can do.
So this technology solved the fundamental problem of physical size. And in doing so, it basically unlocked the entire AI revolution. It leaves us with a really fascinating question to think about. Now that we can build processors of almost unimaginable scale, what previously impossible challenges, in science, in medicine, or exploration, will this Lego-like approach help us conquer next?